Hello, my name is Dallin Albright, and tonight we're going to be learning about conditional statements. Now, part of learning how to take the LSAT is learning about logical reasoning, both for the logical reasoning portion of the test and for the logic games section of the test. And a fundamental principle or a fundamental tool of logical reasoning is what we call conditional statements. And a conditional statement is basically a statement where if we have one condition, if we have this, then we must have another condition. These are called the premise and the conclusion, but they're also known by a bunch of other keywords that we're going to be talking about. So if I have this premise, then I must have this conclusion. One example is if it is Tuesday night, then I will go running. If I take this argument, this conditional statement to be true, then I know if it is Tuesday, then I must go running. Now, if we have this conditional statement, our brains want to immediately assume a lot of other things, and we need to be careful because those other things aren't necessarily true. If this is true, then I might assume if not P, then not C. Or in other words, if it's not Tuesday, if it's Thursday, or if it's Wednesday, then I don't go running. And notice this is not necessarily true. It might be true. I might not go running on Wednesdays, but just because it's not Tuesday doesn't necessarily mean that I'm not going to go running on a Thursday or a Friday. Okay, and so this first assumption that we make is not necessarily true. That's supposed to say if. Another one that we might assume that is not necessarily true is if I have my conditional statement, then I must have my premise. In our example, that would mean if I go running, then it must be Tuesday. And this is false for, or this is not necessarily true for the same reasons that this one isn't necessarily true. I might go running on a Thursday or on a Friday if I feel like it. Another way to envision conditional statements like this is as a Venn diagram sort of thing, where I have a circle of all the instances of C, my conclusion, and all of the instances of P exist within that larger circle. That way, if something exists within this condition, then it must exist within this condition as well. Within the circle of every night that I go running, every time that it's Tuesday night, that exists within this larger circle. But that doesn't mean that there aren't instances that I go running outside of Tuesday night that don't still exist within this circle of nights that I go running. Okay. And this is sort of where the language of the test comes from, because we call these conditions on the left hand side sufficient, as in they are sufficient for us to know that this condition is true, not with these examples, sorry. If this condition is true, that's sufficient to know that this is true. And if this condition is true, then this is necessarily true. So that is the necessary condition. Notice if, however, C is true or P is true, then these are not necessarily true. Okay. All right. There is, however, one thing that we can extrapolate from this initial statement that is correct and must be true as well. And that is, if not C, then not P. Right? It's the inverse and swapped around. So this is called a contrapositive. And if this initial statement is true, then this must also be true. To demonstrate that, we look at our example. If I didn't go running, then it must not be Tuesday night, because there's no way that I can put an instance outside of this running circle and have it also be within my Tuesday circle. So if I don't go running, then it must not be Tuesday. All right. A few keywords that we want to look out for on the test as we're looking at this are, we have our premise and our conclusion. These will be if statements. These will be then or must is a big one for the test. And sufficient and necessary. And then another one is only or only if, indicating a conclusion. And this will often be called either an argument or a statement, but very rarely, if at all, will the test ever actually call this a conditional statement. All right, so the big question is, how does this actually apply to the LSAT? How can I use this argument structure, this notation, to help me get answers right on the test? And we're going to illustrate that with an example question. And this is from an actual LSAT. The Asian elephant walks with at least 2 and sometimes 3 feet on the ground at all times. Even though it can accelerate, it does so merely by taking quicker and longer steps. So the Asian elephant does not actually run. The conclusion drawn above follows logically if which one of the following is assumed. And notice our example answers here can all be rephrased as if-then conditional statements. So I'm going to take a look at the facts that they've given us and their conclusion, and then I'm going to compare that with the conditional statements that they've given us right here. So in the question stem, it tells us that the Asian elephant walks with at least 2 and sometimes 3 feet on the ground. All right. And even though it can accelerate, it does so merely by taking quicker and longer steps. So it can accelerate by taking bigger steps. And then their conclusion is the Asian elephant does not actually run. That looks like an N, but we're gonna work on that. Okay, so our first answer choice says, if an animal cannot accelerate, then it cannot run. And notice the second part of that lines up nicely with the conclusion that they've given us. Okay, that it cannot run, but the first part, the premise is if an animal cannot accelerate, then it cannot run. But notice within the problem itself, we were given the information that it can accelerate by taking bigger and quicker steps. And so this does not fit into this part of the premise, and answer A does not work as the answer to our problem. It does not logically follow from this conditional statement. And so we're going to move on to the next answer choice and see if it fits within the next one. Answer B says, to run, an animal must have all of its feet off the ground at once. And so I see from this, it uses that keyword must have all of its feet off the ground at once. And notice this conclusion doesn't line up neatly with the conclusion that this statement wants to make. But if we look, to run, an animal must have all of its feet off the ground at once, we can interpret that as saying, if an animal is running or can run, then all feet have to be off the ground at once. And we can then take the contrapositive, we can flip that around and say, if not all feet are off the ground at once, then not running, or the animal cannot run. And so if we take a look up at our information, the elephant always has 2 feet on the ground at any point. And so it falls within this category of not all the feet coming off the ground. And therefore, the conclusion that we're looking for, that the animal cannot run, matches up with the conclusion in the paragraph that the Asian elephant doesn't actually run. And so B would be our correct answer. Now on the test and in class, I would normally go through every single one of these possible answer choices just to be sure that we have the right one. But since this is just a demo, I'm going to end it there and conclude by showing us those statements that were so important to us, right? If we have a conditional statement right here, then we can properly conclude that if not the conclusion, then not the premise. Whereas these other two within the middle, if not P, then not C, and if not C, or if C, then P, are not necessarily true. Thank you for watching, and please join the class. Have a good night.